Enough nuclear power to destroy the human race several times over.
This is the Universal Guided Missile, 133 Trident II, an intercontinental ballistic missile that suddenly appears in the ocean after rising 40 meters through water, defying physics. Before it even falls back, its solid-fuel rocket motor ignites and the missile begins its supersonic journey into space. Then, once in space, the missile starts looking for stars as reference points so it can reorient itself and navigate. After traveling for about 12,000 kilometers, that's right, more than 12,000 kilometers, a sequence of events will happen very quickly, but it's known that, when it falls, more than 5 different cities will be partially destroyed. An event that would claim the lives of more than 2 million people, with over 6 million others suffering third-degree burns and being exposed to lethal doses of radiation. All of this with just a single missile, and all this technology was achieved back in the 90s. But what is Trident II? In 1971, the United States Navy began a series of studies on an advanced long-range underwater launched missile system known as Undersea Long-Range Missile System, Undersea Long-Range Missile System. The Undersea Long-Range Missile System program included a long-term modernization plan that proposed the development of a missile with a much greater range, called Undersea Long-Range Missile System 2. It was supposed to reach twice the range of the current and existing Poseidon missile. This Poseidon was an intercontinental ballistic missile that was launched from submerged submarines. This was one of the key features of the missile, which allowed the entire launch to remain secret and difficult to detect, as well as to intercept. Other Poseidon features included a 4,600 kilometer range, greater payload and higher speed, up to Mach 19, about 23,300 kilometers per hour, better accuracy, and most importantly, the Multiple Independently Targetable Reentry Vehicle, or Multiple Independently Targetable Reentry Vehicle, a truly diabolical technology that would change the world forever. This technology was highly secret at the time. In May 1972, the term Undersea Long-Range Missile System 2 was replaced by Trident, with the name being a reference to the trident, a weapon associated with Roman and Greek mythology, often depicted in the hands of Poseidon, the god of the sea. The Trident is the maritime component of the so-called United States nuclear triad, which also includes the land-based Minuteman III intercontinental ballistic missiles and strategic nuclear bombers, like the B-2 Spirit, the world's most expensive airplane. This triad gives the United States the ability to launch a nuclear attack as well as to retaliate from 3 different points on Earth, that is, by sea, by air, and by land. The Trident would be such a large missile that a project had already begun to build a new family of nuclear submarines, called the Ohio class, exclusively made to carry them. Each of these submarines, which are the largest submarines in American territory and are powered by nuclear propulsion, currently carries 20 missiles. Trident II. Originally developed by Lockheed Martin Space Systems, the Trident II is 13.5 meters long, has a diameter of 2.1 meters, weighs 59 tons, and has an estimated range of 12,000 kilometers. Its exact range is a very well-kept secret and is known only by a few people alive. And it has a maximum speed of 29,020 kilometers per hour, or Mach 24, which means 8 kilometers per second in the terminal phase of flight, and it has an accuracy of 100 meters. The Trident II is a 3-stage rocket, each stage containing a solid fuel rocket motor and components to hold the ignition of its engine. And the thrust vector control system, or thrust vector control. We'll soon understand what this system is for. Both the first stage and the second stage are important for maintaining the structural integrity of the missile. Trident uses a fuel called nitrate ester plasticized polyether 75, an acronym for nitrate ester plasticized polyether. and the 75 indicates that the fuel contains 75% solids in its composition. These solids are high-melting explosive aluminum and ammonium perchlorate. This fuel can be stored for more than 10 years. Between the stages, there are interstages, which are the periods separating them. The second one, higher up, contains the equipment section, or equipment section. It's in this section that you'll find the batteries, command sequencers, inverters, firing unit, flight termination system, among others. It also includes the third stage thrust vector control system, thrust vector control, and key avionics for flight control and guidance, like the extremely important MK6 navigation system, which is the true brain of the missile. And here I want to open a small chapter so we can understand the dimension and level of complexity of this system. The MK6 guidance system was developed by a United States Navy program called Fleet Ballistic Missile, and it took 10 years of improvements to reach the required level of precision. The MK6 consists of two sections: the Inertial Measurement Unit, IMU, which contains inertial instruments mounted on a stabilized gimbal platform, and the Electrical Unit, or EA, which contains computers and supporting electronics. The IMU is a 4-axis stellar gimbal platform with a stabilized beryllium spherical membrane. It is mounted on two 2° of freedom gyroscopes, 3 pendulous integrating gyroscopes, a reflector telescope, and a charge-coupled device star sensor. The EA electrical unit contains 6 dedicated computers for gimbal controls, monitoring, and missile orientation and navigation calculations. All these systems allow the missile to know with extreme precision its speed, acceleration, position, and angular orientation, inertial forces, inertial torques, external forces, trajectory, inclination, and much more information before and during its flight. All of this allows the missile to have absolutely zero dependence on external information, such as radar, global positioning system, or star sightings. The MK6 was regarded as one of the most accurate purely inertial systems in the world when it was developed. This, in the late 80s, was able to measure and detect movements on the angstrom scale, that is 100 picometers, which is equivalent to 0.1 nanometers, and in addition, it can detect nano-Gs. But if the MK6 doesn't rely on external info, why did I say at the start of the video that once in space, the system searches for stars to orient itself? The reason takes us back to the late 60s, when American submarines carrying nuclear weapons started getting lost. When they submerged, gyroscopes and other inertial systems recorded all the submarine's movements, and with that, they were able to precisely determine where the submarine was. However, small errors accumulated in the systems, and when they appeared, the crew was lost. The Navy's answer to this problem was to launch Global Positioning System satellites. So when they surfaced, the systems would pick up the satellite signal and recalibrate the systems. The same principle is used in the MK6, but instead of using a Global Positioning System signal, although that's also possible, stars are used as a reference. And it's also in the equipment section that you'll find the Multiple Independently Targetable Reentry Vehicle platform, or Multiple Independently Targetable Reentry Vehicle, which means multiple reentry vehicles with independent targets, which is an exo-atmospheric platform that contains computers, gas stabilizers, avionics, and all the electronics needed for self-guidance. These reentry vehicles, which on the Trident II can be 1 or up to 14 of them, have a cone shape. This shape allows the vehicle to be more aerodynamically stable and handle things better. With the terrible phase of atmospheric re-entry at more than 28,000 kilometers per hour, the black color is actually an ablative thermal material so that it can survive the terrible temperatures during atmospheric re-entry. Inside them is the actual thermonuclear warhead itself, in other words, the atomic bomb. These MIRVs rest on a platform called the base. This base contains a small engine that, once in space, is activated, allowing the platform to perform maneuvers, ejecting each multiple independently targetable reentry vehicle on a different trajectory or orbit from the others, allowing each multiple independently targetable reentry vehicle to head toward and fall in a different place from the others, and the distance separating the impact points of each multiple independently targetable reentry vehicle is a closely guarded secret. The nose cone sits above the MIRVs, encapsulating and protecting everything while streamlining the missile. And on top of it, there is an aerospike, which is a retractable device used to reduce drag at supersonic speeds. Because the rocket's nose doesn't have a very aerodynamic shape for these kinds of speeds, this device works so well that it reduces drag by 50%. However, during the missile's design phase, the engineers encountered a series of problems. Among them was how to make a 59-ton missile with parts that need to detach and separate during flight, hermetically sealed. Since the missile has to be launched from underwater, what system will propel the missile from when it leaves the submarine until it's fully out of the water? The first problem was solved by pressurizing the missile. The Trident II is pressurized with nitrogen, preventing seawater from entering any internal part of the missile. This could damage or add weight to the missile, causing stability issues. The launch of the Trident only happens by order of one person, the President of the United States, with the Trident, just like the other two components of the triad, being the last resort if absolutely everything else fails or does not have the desired effect. This order can be issued using this briefcase, popularly known as the nuclear football, a briefcase that is taken wherever the president goes and whose contents are highly secret. After this order is received by the submarine, a group of officers must authenticate the message by reading and comparing secret codes. Once this phase is completed, a sequence of events will happen very quickly. First, the Mark VI Navigation and Guidance System, or MK6, is initialized, and the specific mission trajectory is loaded into the onboard computer's memory. As soon as the launch command is given, the submarine hatches open, revealing a seal that prevents seawater from entering the missile tube. This seal is extremely strong and robust. It is capable of withstanding a pressure of more than 5 ATMs, or 73.5 pounds per square inch of seawater pressure, with the submarine at 40 or more meters deep. Then, a steam generation system is activated. This system uses a small rocket engine in a separate compartment of the missile, whose exhaust is directed to boil water in a tank. Almost instantly, all that water boils and turns into steam, and it travels along a pipe, where a valve remains closed almost instantly. A command is sent to blow the top seal, and simultaneously the valve opens to release steam entering below the missile tube. The force of the steam is so great that it ejects a missile with enough speed to travel more than 40 meters through water until it is completely out of it. After leaving the water, other sensors and inertial motion sensors confirm the missile is fully out and starting to fall. Then, the first stage engine ignites immediately before the missile falls back into the water. Moments later, the aerospike extends and the missile continues its flight. The thrust vector control, or thrust vector control, is also activated at the moment of launch and allows the engine to gimbal in order to make corrections during flight. When the third stage is activated about 2 minutes into the flight, the missile is already traveling at about 21,600 kilometers per hour, or Mach 18. Once in space, the astro-inertial guidance system begins to search for stars, to correct small errors in speed and trajectory caused by uncertainties in the submarine's navigation systems during launch. This is done by a special camera on board the missile, which looks for just one known star that must be in a specific position. If the star isn't centered in the camera's view, the inertial system isn't accurately calibrated, and a correction is applied. Subsequently, the third stage is ejected and the missile is already on a suborbital trajectory, with only the base containing the MIRVs remaining. The boost, also called the post-boost control system. It then executes multiple maneuvers, moving into various trajectories and orbits, ejecting a multiple independently targetable reentry vehicle in each targeting a separate destination. The way the boost maneuvers and ejects the multiple independently targetable reentry vehicle S in orbit, as well as the range of horizontal dispersion between each multiple independently targetable reentry vehicle, remains highly classified information. Inside these MIRVs, there could be a W-88 type thermonuclear warhead weighing 360 kilograms, 1.75 meters in length, and 55 centimeters in diameter, an explosive charge made of uranium, tritium, and deuterium. It can release an incredible 475 kilotons of destructive power. For comparison, the Little Boy bomb that exploded over Hiroshima had only 15 kilotons, and the Fat Man bomb in Nagasaki had 21 kilotons. If one of these 475 kiloton bombs were to fall on downtown Los Angeles, California, in the United States, the damage would be terrible, with more than 444,000 deaths and over 1 million injured. The yellow circle in the center indicates the diameter of the fireball, which is estimated to be about 1 kilometer. Anything here is vaporized. The second circle, roughly 5 kilometers from the explosion's epicenter, marks moderate blast damage. In this region, residential buildings collapse and everything catches fire. There are simply no survivors in this area. The third circle is the range of thermal radiation about 9 kilometers from the epicenter. All people in this region will suffer third-degree burns, often requiring amputation. In addition, they may develop cancer. And finally, the light damage from the explosion. House windows here will shatter, and atmospheric overpressure will reach about 1 pound per square inch. And how much does a Trident II cost? Well, before we know its price, it's worth knowing what safety mechanisms it has. Since it's a weapon that contains atomic bombs, there are several self-destruct and flight termination mechanisms, and the first one can be activated at a more critical and complicated moment, which is during the launch from the submarine until it breaks the surface of the water. If there is any failure, for example, if the missile doesn't rise enough to safely break the surface of the water, the missile has a mechanism to self-deactivate. If, for example, there is an engine failure during flight or the missile deviates too much from its trajectory, the missile can be self-destructed. This will not cause the atomic bombs on board to explode. There are also other mechanisms that ensure these weapons are safe. What about its price? The construction program cost $26 billion in 2022. And each missile unit costs $30.9 million.